So I hope my screen is visible. Okay.
Yes, it is.
Okay. So good morning to all dear participants and the organizer of this program. So today we are going to start the e-mobility and the possibility of designing the electric vehicles and testing of electric vehicles in Typhoon Hill. So far, you have seen the availability of the applications relating to power electronics and the microgrid and the basics of a Typhoon, how to use the Typhoon software in the virtual environment and in the real-time simulation also you have gone through. So now today we are going to another domain, that is the e-mobility, or the, I should say, the usage of electric vehicles. And the remaining and upcoming 2 days, for today and complete for tomorrow, we are going to talk about on electric vehicles only. So today I'll just throw a light on the provisions available in the Typhoon Hill in e-mobility. Then after this, I'm going to design and simulate one electric vehicle signal processing model, and it is all itself a very lengthy model, and it takes around 2 days, today and tomorrow complete. So be with me while I am drawing, I will drawing the same. So if I talk about the e-mobility, so how you can go, let me start from the scratch. Simply you have to type on the Google Typhoon Hill. After this there will be the icon of Typhoon Hill homepage, and if you want to find the things available on e-mobility, you can go into the solution and go to e-mobility. Okay, once you go to this page, you will be redirected to this Typhoon Hill e-mobility page. And so let's talk about the e-mobility and what is the possibility in the Typhoon Hill about e-mobility. uh, what basically, as you all know, Typhoon Hill environment is for the testing and developing purpose for the controllers and all. And here you can say in the solution, so like in for the hill is for the high fidelity EV and e-mobility models. And what you can do is here in this you can design and test your algorithm for which you are just designing for your electric vehicle. You can do the control designing here, and you can validate it. You can test it in the Typhoon Hill environment, and you can go for the interpolability testing as well. So just start to from the scratch, and let me give you some idea about it. So Hill is basically for electric vehicles and as well as for e-mobility. In this, our hardware in loop solution basically compromises for the designing and the testing of power electronic controllers and for the electric vehicles. And it provides the solution for the electrical drive trains and as well as the EVSE, that is the electric vehicle stationary equipment, that consists of we can say DC chargers or onboard electric vehicle chargers, hybrid trains, and DC-DC converter. It all comes under the category of EVSE. So we you can use Hill for this as a controller or as for testing your developed controller. This is what we have already taken in the very first lecture. Yeah, I'm not going to do this, show this. Yeah, now Hill for electric drive train. So here I should say that you can design the controller for at a high frequency of power converters around with 200 nanosecond real time simulation step down and 3.5 nanosecond digital input over sampling time. And you can simulate the IGBT and MOSFET losses in real time with with calculation for every semiconductor and switching transition. And you can visualize and record all the signals with high resolution in the is capture and scope, as you have already seen in the various examples. And for just simulating the converters, you can drag and drop the 2 level 3 level converters, and you can design your own topologies. If you talk about the third party software, you can import your machine parameter directly from FEM tools like JMAG. If you have the model which has been designed in the JMAG software, that you can directly import to the Typhoon Hill. As you are able to see in this figure, in the design and the simulation tool, the JMAG model can be imported into this Typhoon Hill, and we can simulate the electrical machine with coupled thermal models also. There are examples also available on this thermal model. So this is the possibility of for integrating with Typhoon Hill with the other software like JMAG, FMI, and Zeiss also you can do in this. Now, for if I talk about the onboard chargers for the electric vehicle, you can go for this application also. For onboard chargers, you can deploy your onboard chargers control algorithm, and can simulate your DC-DC power converters with a switching frequency around 300 plus kilohertz in the dual active bridge fashion, and in LLC resonant full bridge. And you can easily simulate parallel configuration as well for multiple DC-DC converter. And for like we know very well, in the electric vehicle generally we use the communication protocol, that is the CAN bus, that is controller area network. There is also a possibility of assessing the controller area network. And you can go for the testing, use DC-DC hill models for vehicle software integration test. As I told you, like with the JMAG and FEM and Zeiss software, you can go with this. And if you want to go in detail, if you want to go into detail, then you can directly click on the tab which is available. Say for example, if you want to go in the DAB application note, simply click on this and you will be redirected to this page. And in detail you can go with this, and there is an example available with us in Typhoon Hill. And you can go with all this as per your uh, uh, you know uh, application on which you are working on. And now if I talk about the hill for electric vehicle stationary equipment, that is EVSE. So one can develop and test electric vehicle stationary equipment for power electronic controller with the high fidelity converter models. And you can develop the same EVSE and design and test it as well. And you can use high fidelity hill models of EV to test your EVSE. And also, like in the very first lecture, you have been told about the power HIL and CHIL. So you can deploy PHIL to test interoperability with different EVs. And here I can show you the some of the feedback which has been given for the which are given by our client. And if I talk about the for battery management system, so yeah, there is a possibility of the battery management system also, with the scalable Typhoon Hill architecture. Scalability means like you can connect the number of devices in parallel fashion of Typhoon Hill devices. If your requirement of core gone beyond one hill device, then you can connect in parallel fashion also, one or two or three devices in 606 series. And for battery management system, you can also use it like for battery management electric controlling unit, you can design as a controller. Then you can communicate it with the CAN bus. Yeah. Then you can do the just measurement and go for this emulation. So there are a lot of stuff available as per the requirement. I'm not just going and in the deep. Actually I need to design a very big model today and tomorrow. So I will focus on this more. I will devote my time on the model designing and drawing, so that you can get an idea how to design an electric vehicle. So with this, I just want to show you some of the feedback of our customers. Like he Mr. Sorry, Dr. Ronald Griul, he is the from BU electrification and racing test system. And according to him, he is saying that due to early porting of control algorithm to the corresponding real hardware, many problems, especially in the configuration of control hardware, can be solved before system integration. This bring considerable advantages in the terms of the development times and cost. So this is the feedback of our customer from from the BU electrification. Okay, this is HVC system. I'm not covering it. This is the success story. And one of the R&D engineer in Honda is using they have used our Typhoon Hill is for testing purposes. And as you are able to see in this rack, you are able to see the Typhoon Hill is placed over there. And according to him, he's saying that we love how easy it is to make changes to the model. and how quickly you can compile a model with Typhoon Hill. Is this is the feedback of Mr. Rohita Kitemato, R&D engineer of Honda. And this is already has been told to you that testing and automation with Hill tomorrow, and the last lecture we'll show you about the testing purpose, how to test your control algorithm, your design model in the Typhoon Hill test ID, as it is available in the Typhoon Hill control center. It has been told to you in the very first lecture, but in the detail and the deep how to run your design model in Typhoon Hill environment, this I will show you tomorrow second half lecture. So you can you can test your design model. You can generate report in the Typhoon test ID environment, that I will show you tomorrow. So this is basically the integration of like Typhoon with the different variety of softwares like Allure. In this Allure we generate our reports, and in the test automation reports we generate here. Tomorrow I'll show you interpolability testing. Yes, as I told you, you can do the interpolability testing, that is the end-to-end testing for the any equipment of the electric vehicle, that is for charging interface and other standard solution. You can have this in our Typhoon Hill environment. And the test for existing standard is available like J1772. It is nothing, simply a charger for the electric vehicle, and that is available on, that is based on the IEC 62196 standard. This there is example of this model of AC charging. I'll show you tomorrow. I will show you the AC charging model as well as DC charging model as well. This is based on these standards, and particular this J1772 charger based. And here's the example for the same AC charging model example. It is available in Typhoon Hill, and the AC charging EV model demo video is also available. You can go through this. I'm not just clicking on it. So this is basically about the possibility of provisions, I should say, in Typhoon environment for electric vehicles. So this is the what basically I have thrown you the light, the what is possible and what you can do in the in case of the Typhoon Hill. And if you have any doubt on this, you can ask. Otherwise, I am just switching to the modeling and simulation of the electric vehicle on signal processing based.
ವಯಸ್ಸಲ್ಲೇ ಮಾತ್ರ ಕೊಡ್ತಾರೆ
Yes, somebody has any doubt? If somebody's has unmuted his mic. Okay, fine. So I hope you all have just opened your Typhoon Hill software so that I can proceed it with the Typhoon Hill software. I have already switched on my Typhoon Hill software, and let me tell you what I am going to do today. Just listen to me very carefully, then you can follow me. So very first of all, what you need to do is you need to open a Typhoon Hill schema, Typhoon Hill software by simply double clicking on it and click on this examples. Very first of all, click on the example. Then you have to go in how to example. Then come down, and there is an example electric vehicle SP. Click on it and open it. Why I am doing so? Let me tell you. Actually, this is the inbuilt example in our library, I should say. This is available, and this is totally based on the signal processing component. The signal processing component are those components which is available in the signal processing library, like the gain constants and the bus joint, bus split, generalized signal processing libraries by which we use to design the controllers. So this electric vehicle is based on the signal processing components only. We have not used any dedicated inverter or motor or converter, nothing else in this model. We have taken the dynamics of for all these components. Like for battery we have taken some dynamic equation, I should say the generalized equations we have taken. And for that motor we have taken the DC motor here, so we have taken the dynamics of the DC motor. And I will let you know when I just start drawing the same. And if you talk about that there is no inverter we have not used any motor. Yeah, this is a very genuine question that we will be covering tomorrow. In that I'll going to show you about the actual example of the electric vehicle where we have used the inverter, the motor, and at the control algorithm, everything we have used in that. So that will be demonstrated tomorrow as per the scheduled in the timetable. That is the last one is V2G and G2V, vehicle to grid and grid to vehicle example. I will demonstrate tomorrow in the virtual environment as well as the real time environment. So let me tell you what is going in this. Say this is basically a electric vehicle, and we are having a lithium ion battery, electric drive we are having, then mechanical transmission, vehicle dynamics, and vehicle control and energy management system. So what we are going to do in this, simply let me show you. Like if you want to show what is going inside this battery, simply right click on it, go to mask and look under mask. This is the one way. Another way is to select it, control and enter. So this is the generalized equation for the battery we have taken. We have just taken the formula for the battery associate implementation that is being given by like 1 upon CIT, integration of 1 upon CIT. We are generating here the battery associated with taking the battery maximum voltage as a constant input. This we are going to design. And here, let me tell you, this is an electrical drive, and in electrical drive just we have framed the dynamic equation of a DC motor drive. How we are just just framing these equations, what are these battery voltage and all this. That I will let you know. I'm going to design this complete model. Again, in the mechanical transmission, we have taken some standard equations and some standard gain ratio. We have designed the efficiency also over there. So this is under the mechanical transmission. Yeah, now let's come to vehicle dynamics. So here we have framed some vehicle dynamics, some resistive force which occurs in when the vehicle is running. So that force we have taken into considerations, like the friction forces and all in this portion, vehicle dynamic. And the lastly is the vehicle control and EMS. Here we have designed the control of vehicle, and like we have taken some LUT table just for the EC driving cycle, what is it and how we are using it. I will come to it when I will start drawing the model. So this is all about the schematic, and I'm not compiling this model right now. As I compile the model, then you will have a SCADA panel in front of you. So right now I'm not going on that. Just I want you to come along with me and just start designing the model with me. Then once you design your complete model, then I want you to compile your model by yourself and go for the SCADA panel. So now for this, what I need to do is, I hope everyone has opened this model on your computer screen, so that I can proceed further. Right now, you have to open it, just because you, if you want, you can take the help. Some say for example, if you lag with me, you can simply go at this tab of yours, and you can see what is going inside. So once you practice with me, then it will take you to the deep inside of Typhoon Hill, and it will make you very familiar. It will enhance your speed for designing your the model in Typhoon Hill environment. So without taking much time, let me come to the designing process. So for that, what you need to do is simply click on the file, as many times our colleagues has told you about it. So open the new model. Okay. And this is for, I am just designing for the Hill 402 and for device configuration ID 1. And just taking going next, and opening a blank schematic model. Yeah, here I am having a blank schematic model here. And this is the electric vehicle signal processing model I have opened along with this, so that I can have an idea. If I want, if I am just lagging somewhere, I can or you can basically take the value of the constants and some other things. So for this, when you just click on this like schematic, and uh, what you have to do is, you have to draw very first of all what this is the lithium ion battery. Very first of all, you have to draw it. And for this, what you need to do is, very first of all, you have to take a subsystem. So just go into the system and drag a subsystem. Yes. And just name it. Say for example, I am naming it as the battery, or I should say the lithium ion battery. So what I am doing, just double click on it and name it. lithium ion battery. Now just double click on it and go inside this block. Delete all this. Yeah. So very first of all, I need to have a constant with me. So what I'm going to do, either you can, there is a two way to fetch the components at your schematic. The first is you can directly go to this block if you know what component available where. So simple is, say for example, signal processing. If I am going into this sources, I can find a constant, drag and drop. Or if you are not able to find it, if you are taking time, simply you can type it constant here, constant constant, then you can drag and drop. Okay, this is also one way. But as I know, I'm familiar like which component available where, so have simply just going into the library, and it's a better practice so that you can be able to find and you can memorize which component available where is the available. Then now I am just naming it as battery maximum voltage. Say for example, uh, I will take its value as 10. So I'm double clicking on it. Sorry, 100. So I'm just taking as, say for example, 100.8, and I'm just taking it as TS. TS is the execution rate, and I will define it in the model initialization when I am done with this. So this is the what battery maximum voltage we have taken, and now what you need to do is you have to completely design this battery. So for this you need to have an integrator. So for example, I am just taking this integrated dragging and drop over here, and I need to have a battery current with me and one product. One product I need to have. So simply type product, and I want the I say for example, let me tell you one more thing. If you want to hide the name of your component, just go for the right click, click on the show hide name. Say for example, I don't want the name to display on the screen, so I can hide the name. And I want is the like the divide and multiply to slash and multiply. I can type in this fashion so that I can have the both the inputs for the division and for the multiplication as well simultaneously. And another is what I just want to have a current, like the battery current. So for this I need to have a signal input port. So either you can go into this port or you can type. So I know where is it available. I am going into port. There is option of signal input port. I have taken this signal input port. Okay, and if you want to flip it, click here. Yeah, this I can, I'm telling again, you can just change this knob, I mean I should say pointer. And I want it to, the name of the single input port is battery current. So be careful while just naming your components. They are just because they are, but with the same name also we can process it in the another subsystem. So I have taken this battery current and I want to like place it at the right side. So just double click on it, and the side it was asking which side you want to place. So here I want to place it on the right side. And index, if you talk about, so yeah, I want to place it on the first index, I mean at the top of the right side. So I've just placed it as a one. So right and one and click on okay. Yeah, so this is what your battery current. And now uh, for the integrator, and I should say for the battery current, it is coming from the electric drive section. So like what I need to have one gain with me. So you can directly type here gain like this and flip it, just assigning its value as -1 because it is coming from the electric drive. So that yeah, this -1. And one more gain I require, and that is for the capacity, the battery capacity. And I am just naming it as capacity, and just give a value The value of this is been calculated and giving to you is 1 divided by 1.4118 E4. Okay, 1 divided by 1.4118 E4. Yeah, and for just for the integrator, now just click on the integrator, and if you want to know more about this integrator, you can go to the help of this. Just double click on it and you can go into the help of the integrator, and it's everything is defined over here, and like it is output value is given by current state plus input value, and what initial value and what initial values it is given over here. Okay, there is a option of external reset and internal. If you want to give from external or internal, you can give it. So this is a very and state port is also given. If you want to initialize the state port, you can initialize, and you can go in detail for this particular component. The everything in every tab, the things are available in the detail, and you can go with it. Okay, so for this right now, I am just for here, I have when I go to initial value, I am just wanted to work in on the external form. I am giving the its input externally, so click external. Okay, I have given the value of the capacity also, and so one more thing I want to tell. Say for example, the initial value of my this battery, I am taking that of 90% is 90% charge. So for example, for creating the SOC also, now I'm just connecting it here, and one more gain I require here. So like rotating it, and this is what the initial value of the battery. Here I am just taking like initial value. I want that to be 90%. Say for example, I just right now 0.90, connect it here and connect it to the initial condition that with this state port and this capacity. Yeah, at this point. Okay, correct the battery current with this and give this sign to this. Fine. And say for example, so battery maximum voltage is done, and this initial value we have taken, the capacity we have taken, and we have connected to this integrator. And again, we have taken this value, the gain value. I just name it as a sign. We are just because we are changing the sign, so I am just typing a sign over there. And now what I want is actually the out, as I told you, the formula for the SOC is the 1 upon C, the capacity and integration of the IT. So the output of this it will be the battery SOC, and for this what I need to have a again I will go to the port and I will take the signal output port. Yeah, and connecting this signal output port, and this I want it at the top of the subsystem. Yeah, top, and at the very first position. So click on the top and one, fine, and just click here as battery SOC. So this is the battery SOC, and the output of this. And now one more output put I require. This is basically nothing, simply the battery voltage, and I want it to be at the right side with the index of 1, and the name it as battery voltage. So I'm just taking it as battery voltage, and this is the output of this. This is the battery voltage. Let me align the same, and I want one more signal output port, so that I want to access this battery voltage at 2 times. So here I am just naming it at again the battery voltage 1, because we need to you can understand by yourself only when I just complete this and I draw the another subsystem. This is battery voltage 1. I am just naming here. and connect this uh, with yeah, actually you have to connect this multiplication with the output of this battery voltage, yeah, and this you can connect here. Yes. So let me check once again whether I have done everything is right. Yeah, this is the starting from the very first, the battery maximum voltage, and this process to the divided multiplier. Yes, initial value 90% I have taken, then the capacity and the battery current we have taken and the sign, and this capacity is going to here, and the initial value is coming to the state port of this battery. This is battery voltage and output of the integrator as the battery voltage I have told, and we need to multiply it with this product, and again this is the battery voltage and battery soc. So now I want one more thing I left here, just I want to measure this battery current at the scala panel. So what I need to do is I need to have a probe with me. So as you have taken the probe and the induction motor designing as Fazlur has told you, and so here you can take the probe to take the signal out at the scala you want to observe. So I'm just taking one probe and connecting here, then just naming it as a battery current, because this is what I want at my battery side, battery current to observe, that is battery current measured MEA, I'm saying battery current measurement. So this is about the battery current measurement. So if you are done with this, kindly let me know. Now let me go to this route, and here you will be able to see uh, this position. Now let me check in this. Actually I think we have not assigned one port properly, because the battery SOC is coming is fine, and the battery voltage, yeah, and the battery voltage we need to give, we have not assigned actually. Yeah, we have to give this the alignment. Yeah, battery voltage 1, it should be top 2, it should come at top, and I want it to come on the second index. Okay, so click again, go back to root and check it. Okay, here let me check. Yeah, battery SOC is fine. Then the battery current, for battery current also, let me check these ports once again. This is right one. Okay, fine. And this battery voltage, it also right one, and this battery voltage is top 2, and this is top 1. Fine, fine enough. So kindly let me know if you have done with this. Yeah, actually we have done some mistake. This is basically the uh, s- signal output port, fine, and let me check once again here. Yeah, signal output port, this is also a signal output port, yes, and this is all signal port. Here this battery current, it should be the signal input port. Yes, it's right, R1. If we go back to the root, let me check here. I want it should come upside the battery SOC is fine, the battery voltage is fine, and this current it should come down and voltage should come up. So let me check with this, because as you are able to see here in the example, your battery SOC, we are also having the battery SOC terminal out, then battery voltage out, yes, and battery current at down point. So I want it to battery current should come at down. So let me check with this battery current terminal. So battery current is basically a signal input port, yes, It should come right side. Okay, and this battery voltage 1, 2. Okay, and this battery voltage is R1. Okay, fine, no problem. We will connect it afterwards. No issues. Now let's. If you are done with this, now let's. y- Now just take the another subsystem, and for that you need to have the electrical drive. So with this, now let me do one thing. Very first of all, just save this. So for saving it, I want it to save in any folder. You can save it at your particular place. Say for example, I want to save in the folder of NIT Delhi, and here let me draw one folder, EVSP. Name the folder SP underscore NITD. Okay, I want to save it here. So now Control S I am just giving, and I want to save it here only. Control C. Yeah, I'm just pasting the location over here. Say for example, I'm naming the file EVSP NITD. Okay, let me save it. So, lithium ion battery is done. Now, let me come to the portion of electrical drive. For this, for that, you need to have the electrical drive one more time. Sorry, one subsystem one more time. So again, go to the system and go to subsystem. Drag and drop the subsystem and just name it as electric drive. Again, double click on it. Delete all this. Yeah. So for electrical drive, what you need to take is that you have to make some dynamics of this, and with the help of this, you can. For this, you need to have some like ports or like electrical ports and all. Okay, so just again go to that ports like input ports, signal input ports. Again, go to this port and take one signal input port. Okay, and with this, just I want to name it as battery voltage, and I want, yeah, just I'm taking it as battery voltage, and this is a signal input port as I told, and I have to keep it as the left side at the first index, left, and the index 1. Yes. Okay, for this again I need a product. Take a product, and for this what I need to do is I need one connect this battery voltage with the input of this product. Just these are the general dynamics of like that DC motor. What I'm Let me show you what I want to do here. Hmm. Generalized equation of the DC motor. This is what I am going to implement here. that the electrical portion and the mechanical portion here. I am just going to simulate all this in the Typhoon environment. So I'm just framing the same. For that, I need now one, sorry, the summer, and for this I want to make some changes here. I don't want to see its name, so just click on it, and the output of this product will be connecting with this. Okay, and now just like take the value of the inductance. I need to have a gain with me. Take one gain block and just name it as inductance, and the value of the inductance is, I'm just telling you, 1 divided by 1 e minus 3. Okay, and this you need to process it with the integrator as per the dynamics of that as DC motor. You might have drawn this several times at your graduation or post graduation level. And what I want to do is just I want to have one register. For that I need a gain once again, flip it, and the value of the resistance is 0.08. Okay, and just name it as resistance. And one EM conversion I need. For that I also need one gain, and just name it as EM conversion 1 first. So for EM conversion 1. Okay, and the value of this is the gain of this is 0.2865. 0.2865. Connect with this. The resistance I have saved, let me check. Yeah, 0.008 resistance value, and just making the loop for the same here. And the resistance output I am just giving to this input of this adder. And one more EM conversion, say for example I want this one more EM conversion. Just I am drawing right now the electrical and mechanical portion of motor altogether. Again, this is EM conversion, and I think its value is 0.2865. 0.2865. Okay, and connect this with this negative of this, and this is 2M conversions. Okay, sorry, wait. Now let me connect it with this. I want some the port, signal input port. Again I'll go to here, and I will take signal input port, and just want to flip it and name it as DCM speed, that the direct current motor speed. So I'm just naming it DCM SPD speed. I want it connect with this, and I want to place it at the right side with second position, second index of position, I should say. Okay, and the output of this EM conversion, for this I need to have one signal output port. Yes, connected with this EM conversion, and the signal output port, this is nothing but simply its drive. When you look into the equation of that DC motor, so this is nothing but simply a DCM torque, and I want to measure this DCM torque. So for this I need to have a probe with me. So take one probe, connect here, and name it as DCM torque. DCM torque. Okay, now done with this portion, and wait, just make a correction. This output of this integrator should come here. Yes, we have connected with this, and this EM conversion is going. Wait, here, and I need to connect it with this. Yeah. Now one more thing, what you need to do is, uh, I need to have one product as well. Now just shift here for my sake of simplicity, just because I need to take this signal. For now here, what I want one more product. So simply type product. See guys, you can get interest in this only once you are just coming with me. Just to, if you are just making this uh, model with me, then you can only get the interest. So I request every participants to draw along with me. It's a lengthy model and will take time. So for this product, say for example, I want the one more signal output port. So here I will just drag signal output port, and I want to flip it, and this is signal output port, and I want it to assign at left side with the second position. Sorry, yeah, and this is what I am just naming it as. This is the current. So battery current one, and disconnect here with this. Okay, now I'm keeping this here, and yeah, here I have taken the DCM torque and DCM speed. And one more thing I want to take here is the back EMF for this. So here I want to have one that signal output port. Once again, let me complete first this portion, and one more, one signal input port. So for this is that this is what does uh, wait this is what DCM, direct current motor battery EMF. So DCM battery EMF, back EMF, sorry, I said MEA. This is what the signal output port, and I want it to place at top second position. Yes, top two. I want to connect it with the this terminal. Yeah, here it will connect. Complete the equation, and one more. This is what the signal input port, and this is the mode ratio, and I want it at top three, and signal input port, and the name is mode ratio. Flip it. Sorry, select it, then flip it. This is the, I should say the signal input port, and it I want to place a top three position. And let me take a probe, one more probe I want. Yeah, take this probe, just flip it, and this is the mod ratio reference, ref, and connect with this, the mod ratio reference, and this is the multiplier. I want to connect the mod ratio reference once with this, and for the second, I want, this is the current. Now I want to take the current, and that current I need to connect at this resistance. Yeah, here. Now let's the circuit is completed now, and this is the battery current. And one more thing, now I want to take this as s- again signal output port. Yes, this is a signal output port. Flip it and just name it as DCM current. M current. Okay, and I want to it to place at uh, top position with an index of 1, T1 DCM current. Yes, this is the SOP, and this is basically what the current which I am just taking here. Keep saving the model. I have just pressed the control S. The DCM current comes. So let me just recapitulate this once again. For example, say here we have taken the battery voltage, and we have now, yeah, this in we need to connect with this. This is the floating terminal. Oh, sorry. Yeah. So battery voltage I've taken with and process it with the multiplier, and I need to have one probe here. Then I need one probe for the measurement of DCM voltage. So I want to connect one probe, and this is nothing but DCM direct motor voltage measurement. Yes, and need to connect with this. Yes, yeah. So here, just check battery voltage. Then we have just taken the signal processing block, simple, followed with that the inductance and the resistance, and we have used this integrator EM conversion, and it will the DCM torque will come to you, and I need to measure this DCM torque, so you can have this. Now the DCM speed we have taken, and it will come from that the portion of uh, that mechanical transmission. You will get to know after this when we come to the the next subsystem. And this is the resistance I have connected with this terminal. Again, we have taken the EM conversion. This we have taken this EM conversion connecting with this, and the output. This is all the this current. We are also connecting this current with this product, and simple. This is a DCM direct current motor battery EMF mode ratio battery current. So now, as I'm done with this, now just save it again and go back to the root and just enlarge it and check it whether we have done everything correctly or perfectly or not.
Excuse me, sir.
Yes, please.
After the product blocked,
Which one? Product block? Which product? The first,
the
this one, this one, or
uh,
this one?
just this one,
Yeah.
push Which block is the next block is called what?
Sorry, this is the product block. Then what do you want to ask?
I mean the upper product. Upper
Ha,
product.
product, upper product. This one.
No, the upper one. The next product.
This one
Yes.
product is here and one product is here. This one you
Yes.
want? Yes, yes,
This
yeah.
product that you are showing to the left, to the right is which block? To the right is which block? To the right. Yes, this block is what? How
This
did
one?
you? Yes,
Yeah.
yes. How did you get it, sir? How did
Yeah.
you? Block?
This is the basically the elder or summer we have taken. Yeah, you can take it. You can type here, na. You can
Where?
here type
Some right?
summer, SUM.
Okay, SUM then.
SUM, double click on it,
Okay, double click.
and
Where is that?
delete this two and keep plus minus minus.
Okay, plus minus minus.
Okay, press it. Okay.
Okay, yes, now it's okay. And
Okay.
then yes, this DCM talk,
DCM talk this one.
the upper one, the last one.
uh, uh, this
This
one.
DCM talk with capital letter talk. Yes, this one. Is
This
it
one.
is
This is the signal output port,
so
and
is
this is the probe.
okay, so it's output, right? Output.
Yeah, you have to write here probe like this, P
Yes,
R O
output.
B E.
Yes.
Okay. Yeah, you
Uh
can take this probe and you can change its name. Simply just change its name. Like,
Understood.
yeah, okay, fine.
Next one is there any difference between rotate and flip?
Difference between?
Rotate and flip.
Yeah. There's a difference. Let me tell you. Yeah. Say for example, just take the one summer only. Just not you can understand some you have taken, right?
Yes.
So if you want to rotate it, and it
Mhm.
will rotate by every 90 degree,
Yes.
90, 90, 90, 90. Fine. And
Yes.
if you want to flip it, horizontal flip is there. That's left to right and right to left. Okay. And
Okay.
vertical flip is there. Say for example, it is like in this position. Vertical flip is this.
Okay.
Okay. 180-degree, if you want to rotate your component with 180-degree, you can simply go for the horizontal and vertical flip. And if you want to rotate at 90-degree, you can go with this rotation, anti-clockwise and clockwise.
Okay.
Okay.
But can I just rotate instead of flip?
Yes.
Does it have any implication on the model? Instead of me to flip, I just rotate.
No, flip for flip na, like this is I'm just clicking in the horizontal flip. Okay. It's having the terminals at input and outputs. Okay.
Yes.
So for at in my horizontal side only, so you can flip it like two terminal plus on left hand side and the one is output terminal is right hand side. So if you do the horizontal flip, this will come like this. Okay.
Okay.
Like this. And if you want to rotate it with 90-degree, like you want the output to come down, just click on
Okay.
it. And again, matlab, both are almost same. That's the difference, only 90-degree and 180-degree.
Oh, it's okay then. Thank you very much.
Okay.
Thank you. Thank you.
So this is about the electrical drive portion. Now uh, let me go out and verify the same, that we have designed the correct ports or not. So for that, just go to the root again. You are having the battery voltage, yes, and battery current, fine. And then again DC, and then you have a DCM BMF. This one, yes, right. And the DCM current also, fine. And the DCM more ratios, they're fine. And DCM speed and DCM torque, yeah, it's very. Let me check this. DCM speed and torque. The torque should come up. I want the torque should come up, and the speed should come down. So just click it. Let's check with the DCM speed. Yes, this is the DCM speed, and the DCM speed is right to okay, fine. And the DCM torque, is basically a signal output port. And R1. Oh yeah, yes, I should place it. DCM torque is right, and 1. That is the DCM torque, and DCM speed is right 2. Fine. Yeah, now it's coming fine. I want the torque to come up and the speed to come down. Now it's coming torque. But just understand the concept. You have to assign the indexing. Which one you want to keep where at what index. So this is what about that the drive position. Okay, you're fine. So now we have done with this two subsystem, and as you are able to see here, and just we need to have the another subsystem, as you are able to see in the example folder. This one, you need to have a mechanical transmission. How these pictures will come, I will let you know at the end. When I complete my model, I will let you know how we can have these pictures in the subsystem. This might be the question in your mind. So now we need to design the mechanical transmission. So for the mechanical transmission, again, what you need to have, you need to have a subsystem with you. Okay, just go to system, subsystem, name it as mechanical transmission, and we will start drawing this mechanical transmission. So just click on this. Type is mechanical as transmission. Go inside this, delete this. Okay, fine. So now what we need to draw in the case of mechanical transmission. Say for example, let me show you one thing. Mm, I have one PPT. Wait, just give me a minute. I need to show you something. Yeah, this is the basic PPT with the formula which I'm going to use. Like here, we are having the resistive forces, the direction of movement, and here we need to incorporate these components like motion resistance and all. Okay, so we are having the resistive forces over there, and we will incorporate these formulas in we need to have the rolling resistance, grade resistance, aerodynamism force. We need to have and acceleration force. These are the all the factors which we need to take into consideration while designing any electric vehicle. So this is what we need to take into consideration. Likewise, grade resistance, gross vehicle resistance, and all. uh, yeah, these are the formulas, basic formulas, and the equations of motion. It has been written for the the electric vehicle motion, and for the mechanical transmission, these are the motion conditions we are taking into consideration. And for this, we need to have some, if vehicle is in stationary condition, then F net is 0, means F tractive equal to F resistive. And if you want the vehicle should be in come in the accelerating condition, for this we need to have the tractive force should be greater to the resistive force. And if we want the vehicle to get decelerate, so for this we need to have the tractive force must be less than the resistive force. So these are some conditions that we are going to frame out in our schematic model, and these are the general formulas which we are going to implement. Okay, like the wheel RPM and all. And this is a transmission, for we need to have some transmission formulas. This we need to incorporate here. So now, without taking much time, just let me minimize it and come to my main window of schematic, where it goes. Huh? Okay, mechanical transmission. Yeah, yeah. Mechanical transmission. We have taken the subsystem for the mechanical transmission, and very first of all, I need to have a signal input port with me again. So I need to again go into the signal input port, and just name it as rake force and I want it to be placed at the top with the index 1, top with 1 index. Okay, and right now I say for example, just for the sake of the dynamics, I need to take into incorporation, and I right now I don't want to use it. So what I will do, I will just terminate this. I need a termination with me. So I right now I don't want it to use, so I am just terminating this signal. Just sorry, I want to hide it name. Yeah, hide it. Terminate this signal terminated, and now I need to design the efficiency block for this. So again I need to have one port, that is the signal input port. I need to have, again I'll go into the port and I will take the one signal input port. And for the signal input port, this is what I am just taking into consideration, the DCM torque. Okay, and I want it to place at the left side with the index of 1 DCM torque. And another, I need to have one subsystem with me, that is the subsystem of efficiency. And for this I need to have one more subsystem, and I'm just naming it as the efficiency. Just get into this, delete this. And for this, what I need to have in the efficiency subsystem, uh, I need to have a switch, that is the signal switch I need to have. So for this I need to have a signal, right? Just type signal switch, signal. Yeah, this is the signal switch I need to have. I require it, and for this, just click on it and make it, I want it to control should be greater than equal to threshold and 0 and inherit. Yeah, I don't want to make any changes in this. And for this I need to have uh, the gain, the input port. Very first of all, the input port, that is the signal input port again. So again I'll go into the port and I will take this signal input port and just name it as input. I just want to name it as input, INP, sorry, P. And this INP is basically, I want to place it at the left side with the index of 1. Okay, and I want to process it with the help of one gain. So for this I need to have a gain with me. This is the gain, one more gain I require. So the gain 2, and here just connect this gain with this, and the value of this gain is 0.92. And say for example this is for the traction braking, so I am just naming it as traction braking. uh, Braking, and its value is 1 divided by 0.92. Okay, connect this with the first input and this with the second input. Okay, and just name, I want to name it as a switch only, just keep it as a switch. Okay, connect with this, the gain which I want to process with this, and I what I need to have one signal output port. So again I'll go to the port and I will take the signal output port with me, and I one more termination I require. So here I will take one termination, and I just want to hide it, hide the name. So connect it with this, I want to terminate it, and this is was the output port, so I am just simply write it as out. Okay, and I want it to place at the right side So then write and at one index, write one, yeah, so output port, and just connect it with this. Sorry, single bubble, yeah, and connect with this also. Yeah, so for example, like this, I want it to place. Fine. So this input is done 0.92 0.92, and this switch is done with this, and the output, just let me check once again. Right side one I want to place it, and with this also left side one signal input port, and I have to terminate this. Yes, fine. Actually this is a big model, so I need to check at every step so that it can help me out at the time of compilation when I face any error, if any. Yeah, just go back to this mechanical transmission, then we will have a subsystem of this, and I need to connect this DCM torque with this input, and for this I need to process with one gain. Keep a gain again here, connect with this, and just click on, just give the value 15.0654. I want to hide its name, and just wheel I just is the nothing, simply the wheel friction force. So what that I need to have one signal output port, connect with this, name it as wheel friction. WH is indicating is here a wheel friction force, and place it at right side with an index of 1. This is done. Okay, and now I need to have one signal output port and one signal input port. So for signal output port I want to flip, and just name it as a DCM speed. This is the DCM speed, add converter speed, and I want to place it on the left side with index 2. Okay, and this I want, just flip it again, and this is nothing but wheel velocity, VLCT, and I want it to place at right side with the index of 1, and want to process with one gain. Take one gain, flip it, hide this name, 15.0654 once again. Okay, so yes, I'm done with this also mechanical transmission. Now let me check out like the appropriate ports are coming or not. Just save it, go back to the root. Yeah, DCM torque for this, yes, one brake force is coming, and the DCM torque at the top, the DCM speed, fine, perfectly fine. Then wheel friction, then the wheel velocity. Yes, the mechanical transmission is almost done. Yeah, now it's better. Okay. Now the one more system, that is the vehicle dynamics. Now let's come to the vehicle dynamics portion here. We have completed this 1, 2, and 3. Now come to vehicle dynamics. So now let's see what's comes under this. So vehicle dynamics. Okay. So what you need to have? Again, we need to have one subsystem. Yes, fine. And just take it as vehicle dynamics. Okay. And for this vehicle dynamics, yeah, what we need to have with us. Yeah, again, there are some blocks we need to take, signal processing blocks. Just go inside it, delete this, then we will start drawing this vehicle dynamics. So for this, what I need to have, very first of all, just keep saving it. uh, I need to have a signal input port for vehicle dynamics. So again, I'll go into the port section, signal input port, and with this signal input port, I want to place it at the left side with the index 1. Okay, and just want to name it as wheel friction force. So here, wheel, yeah, fine. Now I need to have some block and want to create some plus and minus. Okay, process it. Now if we need to take a mass, and the value of the mass will be processed with the help of the gain. Okay, just name it as mass. And the value of the mass is here, that has been taken 1 divided by 692, connected, yeah, connected with the mass and process it with the help of an integrator. Connect one integrator. Okay, and just this is basically go into the vehicle velocity. So for this I need to have a signal output port, connect with this, name it as vehicle velocity. Okay, and I want to place it at left side at the second position. And one more signal output port I require, keep it here. And this is what I want, again the signal for another, the same signal. So I'm just taking as vehicle velocity 1, and I want to place it at the top side with the index of 2. Okay, and connect it with this only, because I want to have this signal vehicle velocity 1, vehicle velocity. This is at yeah, left second, and this is at top second. Yeah, fine, fine enough. Now this is what we are just going to have some another mathematical implementation. So for this I need to have a product with me. say for example, take a product to like flip it, and I want the three input. Okay, and I want a summer also. So for that, I will take summer. Let's just type summer here and flip it, and I want the 3 plus input. Okay, and again here I want one signal switch once again. So signal switch, I want to have a signal switch. Just I want to hide its name and flip around this way. Okay, now what I need to have some forces at input side, at right side I want to take. Say for example, this is done for the vehicle velocity 1 and 2. Now let me take some quantity so that I can tell you better in better way. Say for example, wind speed I want, we need to have as per the calculation, the mathematical calculation. For that we need to have one constant. So we will take one constant. Here I will place this constant and whose value, say for example, I want to flip it first of all, and say for example, right now I'm not giving any value to it, just zero real, and just make it ts, sorry, let it be inherit, and zero. And this is what the wind speed, wind is speed, and it is in meter per second. And right now I don't want it to in consideration, but as per the dynamics concern I need to take it. uh, right now I am just terminating it. If we require it again, I will take the same. Okay, fine enough. So now I need to have a, the one more constant block for aerodynamism coefficient. Here, place here one more for the rolling resistive forces, place here, and one more for the, road slope. Select all the three, make it a flip, because I want to process it at the left side of my plant soil subsystem. So for this, this is what I want to name it as a aerodynamism coefficient. Aerodynamism. Okay, and its value is 0.428. Make it ts, and this is what rolling resistive force, rolling resistive force, and let's say its value is taken into consideration is 135.77. Yes. Okay, and the last is the road slope I want to take into consideration, and just name it as road slope, and that is in percentage I want to take. and right now its value, let's take as right 0 for this time. If you want to have the road slope into consideration, we can give it some value. So this is the road slope. Okay, fine enough. Now just I need to give the value of this vehicle velocity uh, to this. I want to connect it with this. Okay, sorry. Let's make a proper connection. Yeah, shift it a bit. Yes, and again the second input with this. Also, I want to place it there. Fine. And the aerodynamic coefficient is I'm placing here for the calculation, and the output of this product is we need to give this plus rolling resistive force should come in one more input of this, and the road slope for this I'm just processing with the help of a gain, and this is nothing but simply the mass into gravity. So flip it, and just mass and gravity I'm taking into consideration, mass and gravity, and just we give value is a 692 into 9.81 1 divided by 100. Yes, connect it this with this road slope and give it to the input of this. Yes, and let me give the output of this one to this switch, and one constant I require here, and this I'm connecting here, and the constant is nothing, it's simply the static force. Right now this value here I'm just taking like right now 0. Real and execution rate is inherit. Okay, and what I need to do is I want to have one signal output port once again. So what I need to do is I will go to this here, and I'll take one signal output port. Okay, flip it, and connect the output of this with this now. And what is it exactly? This is vehicle resistive force. Okay, and I want to take it at the top one at one point at index 1. This is the vehicle resistive force, and this signal I want to connect it here also, and I want to observe this with a probe. So I will take one probe as well, just flip it and connect this probe with this, and just name it as vehicle force established. Okay, and one thing I forgot to tell, I need to find out one absolute value. So for this, I need to have the ABS. Say for example, now I am taking this ABS, the absolute value. If you want to know more about it, click on it. This is for the absolute value of any input signal. And for this, if you need to go in detail, you can go into this help section, and you need to have the proper, classification and description of this. So just I want to rotate it as like I want. Sorry, I want to connect it here. So just this is the input, and now I want to connect it with the vehicle velocity. Yeah. So I am almost done with it. Let me recapitulate and check once again whether I am missing something or I'm just doing any mistake. So let me check. Yeah, I need to have one probe uh, at this point. So I will take one probe once again here, flip, connect this. Okay, full traction force. Okay, keep saving the model. I've saved it. So let me check once again. Let just back whether check, have you ever just have you assigned the indexing and the naming of every output port? And this is vehicle velocity. Yes, I want to keep it at left side too. And these are the this is the constant, this is constant, this is constant, these all are constants. Basically we are just giving the value, and yeah, this is vehicle resistive force. Let me check it. This is a single output port and the top one, because it create problem at the end when you compile the model, so better to check it here only before going at that point. Fine enough. Or you have example with you also, you can have a look and make the comparison over there. If anybody is facing any problem till now, just you can ask me, you can present your screen, I can help you out there. Me along with my team is we are available here in the session only, so we can find help you out. And if you are facing any problem, and if you are unable to share your screen and don't want to share your screen, you can simply post your query in the chat. uh, Actually it's very difficult for me to view on both the things like the schematic window and the chat. So my colleagues are available, Fazlur sir and the Shamshir sir are available, and Khushbu ma'am as well. They can respond to you if you have any problem and you want to you know post on the chat. You can. Till now, if you have any problem, you are requested to ask me. And if you are not finding any, actually this is what the model is lengthy, no doubt. I agree the model is lengthy, but what we are doing here, just we are just taking the simple blocks, the simple signal processing block we are taking into consideration here, and we are giving the connecting and giving the value. Let me tell you, check one thing. Yeah, here what I have done is, here what you need to do is give the threshold value is zero point 0.5. Okay, so the threshold value is zero point 0.5. You need to give, I forgot to mention, control is greater than equal threshold and value is zero point 0.5. Okay, this is done. Then the mass value I have also taken 0.92, mass and gravity also. Fine, now just go to the root and check, are all the ports, required ports, I mean, coming or not. Yes, so let's check what is going here. Here we need to have a vehicle velocity. Yes, it's coming here. wheel friction is coming, uh, and the vehicle resistive force is coming, fine enough, and the vehicle velocity. ठीक है, fine. So almost four subsystems we have designed, and the last one is the vehicle control and if I'm not wrong, is EMS. That is the energy management system. This is going a bit, the bigger, or I should say the lengthy. So for this, the last one is this, and we need to have this. Now let's start this, and let's see how much we can complete it in 15 to 20 minutes we are having. Then after this, we will just proceed it at after lunch. Okay. So just for this, I need to take one more subsystem. Yes. Yeah, you come at this point and name it as vehicle control and EMS. Control and EMS. Fine enough. Delete all this. So for this vehicle control and EMS, let me take inputs in the form of signal input port and signal output port. So very first of all here, I need to have a signal input port. Yes, let me go through slowly. If you have any problem, you can ask me. So this is, I want to have the battery SOC with me. So let's say, for example, just name it as battery SOC. And I want to place it at the left side with the index of 1. Fine. And for this, I need to have a signal switch once again. Okay. So type again one more time, like signal switch. And this time in the signal switch, what we are going to do is the value of the threshold is take 0.9 in order to find enough. Yeah, we have to keep it here, just move it there. One of the lengthiest block of this, take one gain block, connect with this gain, and the value of this, say for example right now I'm just giving 100, and we are converting into percentage, so just naming it as 2%, and just take one probe, connect your probe here, and just name is at battery SOC established, BATOCEST. Fine. And just hide its name, or this is going a bit complex. Just I want it to get at this point here, connect. Okay, now let's take the input for this. So just take the two constants. I need to have two constant block with me. Type constant, one more, just this is for the electrical braking, and I'm just hiding its name, and for electric braking purpose, electric. Guys, you can ask me, you can interrupt me meanwhile if you are facing any problem. Electric braking, and for this the value right now I'm just taking uh, 0 ps 0. Yes. So okay, fine. Connect with this, and this is also connect with this. Keep it bit fine, and just take one, signal output port. So go to output port, signal output port, and the signal output port, connect it with this, and the name is as brake force, brake force. Okay, and I want to place it at the bottom. Just click on it, go to bottom, and at bottom I want to place it as the third index, bottom 3. Yes, and this is associated with shafting left 1. Fine, just keep saving your model. So this is one portion which is just describing the signal switching over there. Now we need to have a move on. Say for example, let me tell you one more important thing. So for this we need to have one clock, and I want a one lookup table. That is why lookup table is required. I'll let you know 1D lookup table I want. Yeah. So if you come to the lookup table and if you double click on it, so there is an option of like equidistance and non-equidistant and all, and you can use it for the ECE driving cycle. So for this, if you have some data available to you, you can take your data for designing or designing for ECE driving cycle. You can take it, or say for example, if I'll show you, let me show you something. This is basically the ECE driving cycle data which is available with me. That is the value of x and f of x. The function of x is available with me. I have just taken it from the example model only. So it is editable if you want to work in this, and you can copy this particular example folder and paste in your working folder, and you can have your own data as per your requirement. As your, if you have any real time data with you, you can have it. So for this, this is basically the EC driving cycle, and for this what I will do, I am just coming here, and this is the EC driving cycle. I am just copying that full EC driving cycle from this point, and simple control C, and I will do the control V. Either I can go for this, or what I can do, simply double click on it, and I can and make it the non-equidistant. Okay, and you can enter these data, where it coming from. It might be yours, or it is what I have just shown you right now. This was nothing but simply the data which is available in the example EC driving cycle. I have copied from here, there, and pasted here. Either you can copy here and paste there, or you can copy complete driving cycle. So this is what I have just taken from the example model and connecting this EC driving cycle. As I am saying time and again that you can have your own EC driving cycle. Okay, you can connect with this. Now what next will happen after this EC driving cycle, I will tell later. Let me tell you, take some input ports. Then after that I'm going to shut this wind this lecture up. Then we will do the more in our next session. Say for example, I need to have some ports, and now I need to have one signal input port, one more signal input port here, again one more I require, four I require actually. Okay, so for this is vehicle velocity. I am taking from that lower sub blocks H, and velocity, vehicle resistive force H, force. This is vehicle velocity. Yeah, I want to keep it as on right side and with index of 1. And this resistive force I want to place it at right side with an index of 2. And again I'm having this DCM. This is the DCM current, and I want to place it at left side with an index of 3. Then DCM, this is what battery EMF, VEMF, and want to place at left side the index 3. And again one more port I require. Let me organize it well so that there must be some space available with me. Yeah, this is battery voltage. I want to place it left side with an index of 2. Okay, this is done from my side for this block. Right now it is incomplete, and we need some more time to complete this model and to make the connections, to insert the pictures and to go for the SCADA. The SCADA is also very lengthy and it will take some more time. And so till now, if you have any problem, you can ask me. After this, we need to design one controller, that is the IP control. For this, I need to design a controller, and what I want is I want to just stop here, and because it I don't want to left any concept unfinished, so that I would like to start with a new beginning with this controller in the second half. So if you have any problem till now, please ask me. Okay, like say for example the battery SOC, battery voltage, DCM current and DCM BEMF, and now this brake force is coming, vehicle resistive force and vehicle velocity. One mod ratio is also we require. This that I will take afterwards in the second session, then one more input will come over here. So it is this block is still incomplete, I'm saying, and we will do more in the second session after lunch, that is from 2 p.m. And if you have any doubt till now, please ask me. I'm just, or we can wind up here. uh, from the host team. uh,
Yes, Alex.
yes sir.
Yes, sir. I am here only.
Yes sir. I just want to wind up here only, and the model is still incomplete, and I will continue it post lunch, that is from 2 p.m. So if you,
Sure. No issue. Participants may
yes,
seek any queries
yeah,
whatsoever Dr. Salim has covered in the session. Better to discuss right now itself.
yeah,
If you
because
have any
this model will
concern.
take one more day, like in the second half we will do, and tomorrow first half we will also do for this SCADA panel. It's a lengthy model, so I want that if participants have any doubt, they can ask me meanwhile, because it's very difficult to find out the error at the final compilation.
Mhm.
So yeah, if anybody, if you are drawing, you are designing along with me, you can ask me, or you can make a note and you can ask me in the second session on as well. Till now I have done from my side as per my schedule, and I will start in second half.
ठीक है, fine.
ठीक है सर, फिर we'll meet at 2 p.m. in the second session. Okay.
Okay, okay. Thank
Okay
you
sir.
very much.
Thank you
Thank
sir. Thank you participants.